Hi everybody! So in today's video, we're going to be going through Unit 3, Lesson 8, which is an introduction to the mean value theorem. Today, we're going to be looking at one learning target, which says I can justify my conclusions by applying the mean value theorem over an interval. Now, what we're really going to focus on today is just a brief introduction to what the mean value theorem says, and we're going to really try to zero in on the conditions. So what conditions does your function need to meet in order for the mean value theorem to be applicable? Okay, the mean value theorem is the second of two theorems that we will learn this year that are called existence theorems. This means that the theorem will allow us to guarantee that a certain feature of the function exists, but it will not give us the exact x value where that feature occurs. So here are the conditions. A function must meet the following criteria before we can apply the theorem. If the function is continuous on the interval from a to b, and the function is differentiable on the interval from a to b. Now, let's just start by examining those two conditions before we look at the conclusion. So what does it mean for a function to be continuous? Let's start with that. As a reminder, a function is continuous if there are no jumps, removable discontinuities, which we also sometimes call holes, infinite discontinuities, which we sometimes call asymptotes, and that has to be including at the endpoints. That is why you'll see that this uses brackets. That means there can't be a hole at the endpoints, there can't be an asymptote at the endpoints, there can't be anything weird going on at the endpoints or anywhere in between those endpoints. And the function has to be differentiable on AB. Now, differentiable, as a reminder, is almost like stricter than continuous. So differentiable means there can't be any corners, there can't be any cusps, there can't be any vertical tangent lines, and there can't be any discontinuities. Except at the endpoints. So you'll notice that there are open parentheses here because for differentiability, we don't really worry about the endpoints. For example, if there is a corner at the endpoint, it doesn't matter because that's where we're going to stop. So we're not going to look at the other side of the corner. So the endpoints here don't matter for differentiability, but they do matter for continuity. Now, if your function behaves all these rules, it's got to be continuously connected, it's got to be nice and smooth, nothing weird going on, it's got to be differentiable, then we have a pretty big conclusion. We are guaranteed at least one x value between the endpoints. So we're guaranteed this. That means 100% of the time this is going to happen. At least one x value. And we usually call that number the number c between the endpoints such that f prime of c is equal to f of b minus f of a over b minus a. Now, this may not seem like such a big deal, but it is so huge. So here's what this really means if we break it down. F prime of c means the slope of the tangent line at x equals c must be the same slope as f of b minus f of a over b minus a is what we call the average rate of change, or in other words, the slope of the secant line between the endpoints. Here's what that means visually. So let's choose two endpoints. In this case, I'm going to choose -2 and positive 2. So let's say that my interval goes from negative 2 to positive 2. That's going to be from here to here. The f of b minus f of a over b minus a is the slope of the secant line. So we're talking about the line that cuts through the graph and connects those points. What this theorem says is that there has to be at least one place such that the tangent line that brushes the graph has the same slope. Now we can find that using a visual inspection. So if we kind of like try to find a place where the tangent line looks like it'd be about the same, like parallel, it looks like there would be a spot like right here, and possibly even another spot down here. So this would be a C value and this would be a C value, because those would be the x coordinates of the places where the tangent line has the same slope as the secant line. Now we can recognize that we should apply the mean value theorem because we are going to be asked to justify our answer, which means it could be either the intermediate value theorem or the mean value theorem. But more importantly, can you guarantee a specific derivative value? So if we were using the intermediate value theorem, which we learned earlier this year, it was when we wanted to guarantee a specific y value. Here we're going to be asked to guarantee a specific derivative value. So let's take a look at the follow-up questions. Like I said, today I want you to really focus on the conditions. How can you tell if a function is continuous and differentiable? And we need to be able to do this in a variety of contexts, both visual and algebraic. So if what we're going to do for these problems is determine whether the functions do or do not satisfy the conditions of the mean value theorem, and if they do not, explain why not. So condition number 1 is continuity. This function has to be continuous, including at the endpoints. In problem number 1, I'm noticing that there's an issue. The function is not continuous at a. So we would say it does not satisfy because it is not continuous at x equals a, which is one of the endpoints. Therefore, I'm not even going to bother checking with differentiability because I already failed the first condition. For problem number 2, it looks like my function is continuous everywhere. So now I'm going to move on to, is it differentiable? And in this case, I'm noticing that there's a cusp here at x equals 1. So I would say it is not differentiable at x equals 1 because there's a cusp. For problem number 3, I'm noticing that the function is continuous, so it is connected. However, it looks like there's a place where the tangent line would be vertical at x equals 0. So I would say it is not differentiable at x equals 0 because there's a vertical tangent line. And last but not least, for problem number 4, it looks like it's not continuous because it looks like there's some sort of like an infinite discontinuity here at x equals -1. So I would say that this is not continuous at x equals -1. There's some sort of infinite discontinuity. Now, what if we have an equation instead of a graph? So for problem number 5, we need to recognize that when we have an absolute value function, there's going to be a corner somewhere. In this case, the corner is going to be at x equals 3. So the next step is going to be to check to see if 3 is within our interval. Since 3 is between 1 and 5, that means that my function is not differentiable at x equals 3. So I would say that f of x is not differentiable at x equals 3 because there's a corner. In problem number 6, we have a piecewise function. So what I'm really worried about here is sort of the breaking point. I'm going to go ahead and start by plugging the number 4 into the top, which means I get 8 plus 3 is 11, and plugging the number 4 into the bottom, which means I get 16 minus 5 is 11. So therefore, this is a continuous function. Now I'm going to take the derivative and I'm going to try again to make sure that it's differentiable. So the derivative of the top is 2. And that's when x is less than or equal to 4, and the derivative on the bottom is 2x for when x is greater than 4. Now if I plug in the number 4, on the top I get 2, and on the bottom I get 8, which means it is not differentiable. So I would say that f of x is not differentiable at x equals 4. There's going to be some sort of a corner there because we change slopes from 2 to 8. Okay, that's it for today. Thank you guys so much for watching, and I'll see you for some practice with the mean value theorem.